not. But if you wanted to, you could go back and review our chapter by doing a quick glance at videos at some point. We're in the same section today, Chapter 9, Section 1, about congruent and similar figures. Today we're going to focus on similar figures. And so before we do, let's review what a congruent pair of polygons is. Congruent figures have two things in common. They have the same blank and blank. Can you finish that? They have the same size and shape. Okay? Similar figures, the word itself leads you to think that they're not exactly the same, right? They're not clones. So there's something the same about them, and it is one of the two characteristics you just named. It's either size or shape. So let's take a look at these here. This figure here is a star. I can clone it like that. So I could say that these two figures are congruent, and the symbol for that is that, right? Congruent. Kind of has an equal sign with a wavy line. And so then I could take this figure, and because of the software that's been written up for this, I can do that, right? So now this figure, would you say this figure is similar to these clones?
Yes.
Yes. So does it have the same size or shape?
Shape.
It's the same shape. The symbol for similar figures is just a single wavy line, like that. We're going to go write that in a moment over where we're having our little rule box. So that's an easy thing to remember, right? It has the same shape. So what is it about these that we could measure to show the same? When we say same shape, what is the same? Is it the lengths of these sides? Are the lengths of the sides the same?
No.
That's pretty easy to see they're not, right? So what is the same, Jeremy?
What looks like the size of it? I mean, the size of it isn't the same.
The size isn't the same. The shape is. So what gives it the same shape? Lexi.
It has the same points and angles.
It has the same angles, exactly, which is why we have this little interactive protractor here. So I can bring this over, and I mean, if we were going to measure one of these angles, let's measure this one. What do you estimate that angle to be? Does that angle look like a right angle?
No.
Does it look larger or smaller?
Larger.
So something larger than 90 degrees. So someone give me your estimate.
102.
I hear, what do you say, Jimena?
120.
She says 120. Who agrees? Who thinks a little bigger? Who thinks a little smaller? Ooh, a lot of people think a little smaller. So let's go with something a little smaller. Sabrina, what do you say?
110.
110. Who agrees with 110? Who thinks it could be a little bigger? Who thinks it's a little smaller than 110? Ooh, good for you. Okay, so what do you think it is, Tessa?
Maybe like 100 or 100.
Just 100? Who likes that? 100?
Yeah.
We have a bunch of people liking 100. Who likes 110 better? Who likes 105? Ooh, we got a lot of 105. Okay, let's see what it is. If we take this protractor and put it on that angle, we can measure this. And it's kind of hard to see. Let me blow this up a little bigger. I'm going to have to bring this down. Let me get rid of that one. And bring this one down so you can see it. So we're going to put the center of the, oh, it's behind it. Let me bring it to the front. Let me pause the video so we don't. Okay, so we put the center of this protractor right on the vertex. And as I read this protractor, would we be reading the inside degrees or the outside degrees? Can you see?
Inside.
The inside, because it starts at 0. So we would extend the line out here and it starts at 0, which is on the inside in this case, right? And so then we could extend the angle further this way.
105.
And it looks like 100, 2, 4, 6, 108-ish. So 110 was a great estimate. Who said 110? A bunch of people. But you guys were right in the ballpark, right? So good. So if we take this protractor and put it on this angle, what will we get?
110.
We will get the same measure, right? Because if they are similar, they do have the same angles. Okay, so let's go back to our definition. Over here, similar polygons. And we're going to show a sample here of two triangles that are similar. ABC and triangle XYZ are similar. Their corresponding angles are congruent. The second thing we can say is their sides have a relationship. They have a relationship, but are their sides congruent? No. So who can tell us how their sides might be related? Do you remember how they're related, Bella?
They might have the same vertex. Or like the same point.
Two different triangles have different vertices, but how would their sides be related? Anybody? You don't know? Okay, they're proportional. The sides are proportional. So we're going to go and kind of identify that right now with these two triangles. So pause and take this down. Okay, what did we say yesterday we can do if we're given a congruency statement? This up here is not a congruency statement, it's a similarity statement, right? But what can we say we can do when we're given a sentence like that? Remember with our congruent figures? Nika?
You can say that A is equal to X.
Good, so angle A is congruent to angle X. Well, we did this with congruent figures, but now we're finding that we can do this with similar figures, right? And so we can kind of throw out the picture. Don't look at the picture. Instead, come up here and look at the given sentence. And you can find the corresponding vertices, right? So looking at this sentence, what angle goes along or is congruent to angle B? Everyone? Good, angle Y, you can see it over there. So we can make that statement. And then finally, the last angle, angle C, is congruent to angle Z. Good. Now what is new for similar polygons, in this case, we can say that the ratio of their corresponding sides are equal. So we can set up a ratio that is equal to a second ratio or a proportion. So we can again look up here at this statement and say side AB, let's put that down, side AB would be proportional to what side in triangle XYZ? Say it, Katie.
X, Y.
Good job, XY. You can just read it right there. So we can use this statement again to look now at BC, the next side, right? BC is similar to, BC here is similar to, you see, YZ. And there's a third pair of sides, isn't there? Who can name the third pair? Starting with triangle ABC. And you name it, Sophie? AC, she's looking at this side here. Okay, AC is similar to?
XZ.
Good job, XV. And remember, it doesn't matter how you name a segment, you just need the endpoints. So AC equals CA. We're naming the endpoints. Okay, now that we have those ratios set up, we can substitute values, right? Do we know the value of AB? Look up there. Do you know the value of AB? 6. Good. So I want you to go in now and fill in the values for these ratios. Go fill them in on your page and then we'll see what you got. Give us the values now. Tessa, what is it? 6 over what?
3. 8 over 4.
8 over 4.
And 10 over 5.
And 10 over, I don't see 5 up in the picture.
Well, yeah. It
So
would be
she
10.
is predicting that the unknown side here is a length 5. Who else predicts that? Very good. Okay. And how did you know that? Tessa, tell us.
Because the other ratios are all half of the numerator.
Good.
So-
So each of these ratios actually equals what?
2. Or
2,
equals 2.
right? 2. 6 over 3 is 2. 8 over 4 is 2. 10 over 5 is 2. Okay? So we are able to find unknown sides by using our proportions and solving them, and that's what we're about to do. Okay? So let's try that here. You're going to have to pause, take down the information, and prove, are these triangles similar? In order to prove that they're similar, you must show the math. You must show, you may not just write, yes, they are similar, or no, they are not. You must give me the math that proves that they are or proves that they're not. Do you understand? So what math will we be looking for here? How can you prove they are or not? Casey?
Like what they equal, like what each side equals.
Good, you're going to set up those same ratios we just have, right? You're gonna set them up and see, is it true or is it false? Are these similar or not? So that's what you're doing. Okay, so Nico's work is here. He's showing you that these triangles are similar because they all have what looks like a ratio that equals, for his setup, his ratio equals 2. See that? So he went from, he set his up like this, triangle ABD over triangle, how do we name it? KLM, I guess, KLM. Now, that's one way to set it up, and it proves that these triangles are similar. The other way to set it up would be, who did it the other way?
Yeah.
Okay, and so Mary, tell us, which triangle did you put on top?
KL over AB, or AB.
Good, and so over triangle ABD.
Yes.
So you may set it up either way. When you set it up the way Mary set it up, the proportion would not equal 2. It would equal what? 1 over 2. Good. And this proportion equaled 2 over 1. But either one of them will prove that these triangles are similar. The biggest problem would be if somebody put triangle ABD over triangle KLM, and then they did KLM over ABD. That would not be equal, would it? We would have 2 over 1 equals 1 over 2, and that is not true. 2 does not equal 1/2, right? So once you choose a triangle to go in the numerator, it must have all those pieces in the numerator. Never put the small triangle then in the numerator if you start that way. Does everyone understand?
Yes.
Okay. Final question is simply, can you find the missing side? And what else do you notice about this question that makes it a little more advanced? Just a tiny bit more. Who notices? Somebody I haven't heard from today, please? Amanda?
It's missing one of the numbers on the side.
Okay, it's missing a number here, so we don't even know this number. Over here is the missing Z that we're trying to find, and there's another thing that's very different here. Sabrina?
They're turned like upside down.
Very good. So one triangle has a vertex pointing straight down. The other one has a vertex pointing straight up. See that? So this is the way that we sometimes receive geometry. We get things turned and twisted. But what did they give you that is a huge help right now? That you did not even have to come up with. It's a huge help. Sophie? They gave you the sentence. Very good. This is a gift. I guess we should put a bow on it.
It's a Christmas gift.
It's a gift because now you know how to set up your proportions. Okay? So please use your sentence to set them up and then fill the numbers in. Okay? And pause and come back when you're ready to check. Okay, so we're using that beautiful gift, and let's just start by setting things up. We'll start with the left triangle. Let's put the left triangle over the right, right? So we're going to say PQ is proportional to, say it, WX. I want you all to say it. Ready? The next side is QR is proportional to XY. And the final side is RP goes with YW. Now we start filling in, right? PQ equals
30.
and WX.
Z.
Here's our unknown. We're looking for that, right? And QR.
56.
And do you know XY?
35.
We know it. Okay. And then finally we had RP.
36.
We don't even really need this, but do we have YW? We don't know what that is. So when you have these three ratios and you're asked, what is Z? You don't even need all of these, do you? What's the most important ratio given here?
56 over 56.
Is it the first, second, or third?
Second.
It's a second because it has all the known information. That's the one we like, okay? So we can throw this one out. We don't need it. We weren't asked to find WY. This is unknown, but we weren't asked to find it. We simply go solve this one, okay? So let's bring it over here. 30 over Z equals 56 over 35. And what did you do to solve that? I'm going to pause this and you can come back and see. So the class decided to simplify the fraction that was here, dividing both by 7, and then cross products property led us to 18.75. Very good. And there you go.